Okay, as we finish up section 1.3, we're going to be talking about operations on functions. So we're going to learn to identify and apply binary operations on functions, including composition, which is one of the more important ones that will have consequences for us later in this course. Before we get into that, let's talk about what operations really are. And I'm going to use the word binary operations because fundamentally what we're talking about, and we're going to step back and think about real numbers for a second, is that a binary operation, which we can usually think about star, will relate two objects, two mathematical objects, and create some new one. So the operations that we're most familiar with are things like addition, subtraction, multiplication, and division, the big four. And so what's important to remember is that when we say A plus B, right, we're actually saying the sum of the real numbers A and B is the new number that is created from A and B using this binary operation. So if you can think about it as like a machine that takes these two real numbers, A and B, adds them together, and pops out this new number, A plus B, right? And the same thing is true for all of these operations, right? They have special rules, they have special meanings, but ultimately they do the same thing. You get two of them, two objects, and then you get a new one. Something that's also important is they have different properties, right? So for instance, addition and multiplication are commutative, which means it doesn't matter which order you do it, right? A plus B equals B plus A, and A times B equals B times A. But subtraction and division are not. The order matters. A minus B is not the same thing as B minus A. Also, division has one more special rule where B can't be 0, right? Whatever we're dividing by can't be 0. So that also is a consideration here. Okay, let's jump into operations on functions. So all the big four operations will do exactly what we want them to, which is we have fundamentally four of these, right? We have addition. So f plus g is this sum function where we define it as for each x, we take f of x and g of x and add them together, right? So this right here is the sum function. It's a new function, right? And we obtain it from adding the y values together, okay? Similarly, subtraction f minus g of x is going to be defined by taking f of x and subtracting g of x from it for every x that they share in the domain. So this f minus g is what we call the difference function. And it's different from g minus f, right? Our third is multiplication. So we have f times g, which we'll often just write as fg of x. And we define that as you take your f of x and you multiply it by g of x. And this new function we call the product function. Product function of f and g. Lastly, division of two functions. we write that f over g of x, and that's, as you might have guessed, f of x divided by g of x. So you take the two y values and divide one by the other, so long as g of x is not equal to 0. Okay? And this new function f over g is what we call their quotient function. And it's different if you have g on top of f, right? The order matters. Really, really important for domain of your new function. It only makes sense if that x value that you're taking makes sense for both of the functions. So it's going to be the domain of f intersected with the domain of g. So in other words, only the x values that make sense for both f and g are allowed for the new function that we got from operating. Okay, let's work on some examples to see what we actually mean by this. Example. So first off, we're going to write the f plus g, f minus g, fg, and f of g for f of x equals 1 over x and g of x equals x squared. So they're not too complicated functions, but we're gonna put them together. All right, so first things first, f plus g of x is 1 over x plus x squared, because that's the expression for f plus the expression for g. And we can combine this and make this a little bit simpler by just writing 1 over x plus x cubed over x. We're trying to get a common denominator. Add 1 plus x cubed over x. And then 1 plus x cubed is a sum of cubes, so it actually has a simpler form. We can write it as 1 over x, or a factored form, I should say, times 1 minus x plus x squared over x. Okay, so that's the sum function. Okay, the difference function, f minus g of x, is going to have basically the same format, just with a subtraction in between the two expressions that define f and g. And so you might have guessed this means we're going to have something slightly different, which is we're going to have 1 minus x cubed over x, which is a difference of cubes now, and we can write that as 1 minus x times 1 plus x squared over x. So they actually look very similar, and that's a consequence of the specific examples that we chose here. The third step here is to figure out what f of g, or f times g, I should say. That's 1 over x times x squared. And so this means we get x squared over x, and as long as x is not equal to 0, right? So we plug in 0, this is undefined at 0. Then we can write this as just x. Does that make sense? So we canceled a factor of x, but that's only allowed as long as x is not equal to 0. Okay? Obviously, we should note for all three of these so far, x just can't equal 0 in the first place because it's not part of the domain of f, which was 1 over x. All right, so good so far. Now, f over g of x is going to be 1 over x squared, which actually reduces down to 1 over x cubed. Again, x can't equal 0. All right, very nice. So those are the four, actually let me label these differently. A, B, C, D. Okay, question 2. Okay, we're going to have a table here. So f and g are given in the table. Find fg, so f times g of -1. Okay, so here's our table. Our x row, our f of x row, and our g of x row. So -1, 0, 1, 2, 1, 2, 3, 4, and -1/2, -1, -3/2, -2. Okay, so we need to find the individual values of f of -1 and g of -1 and multiply those together. So f of -1, you look at the -1 column, and we find that that f of x value. And then g of -1 is the same value, but in the g column. So that's going to be 1 times -1/2, which is -1/2. And that's our answer for that. Okay. Lastly, last example that I have here for you. Find the domain of f over g when f of x equals square root of x and g of x equals square root of 2 minus x. Okay, so something really important here is notice that f and g already have restrictions on their domain, right? So the domain of f, for instance, we know that x has to be greater than or equal to 0, and we know that for g, we need to satisfy 2 minus x is greater than or equal to 0. This is going to come into play later, okay? So first of all, that's something that is important to note here. But when we form f over g of x, remember that we're going to get a ratio. So whatever's in the denominator also can't be equal to 0. So this will turn into x over 2 minus x, so long as what's underneath the radical in both cases is not negative, okay? So really what we're looking for then is, so domain is all real numbers such that x over 2 minus x is greater than 0. Strictly greater than, because we can't let that equal to 0. Okay. Then, or actually, we can let that be equal to 0. No, we can't. Sorry. I don't know why I wrote that. Okay, how do we solve this? What we can do is we can set up, because this is a rational inequality, okay? So if you're uncomfortable with these, remember that what you want to review is rational and quadratic inequalities. Basically anything that is an inequality that's not a regular linear inequality, okay? But what we want to do is remember this is a rational function, x over 2 minus x. So what we can do is we can set, oh wait, sorry, I know now. This is what I wanted to say. And 2 minus x cannot be equal to 0. So those two things have to be true. But we'll focus on the inequality first. And what we can do is we can think about the factors x and 2 minus x. And we're going to set up the real number line. 0, -1, -2, 1, 2. This is not a great graph, but bear with me here. So our question here is going to be where is the factor x positive, or at least greater than or equal to 0? Well, x is greater than or equal to 0 on this side of 0, and it's negative on this side. It's positive exactly at 0. As for 2 minus x, where is that positive and where's it negative? So it's, if you plug in something like -2, -1, 0, no, sorry. If you plug in anything that is, if you plug in -2, it's positive. Plug in -1, it's positive. Plug in 0, it's positive. Up until 2, and then it becomes negative. So positive, positive, negative, and x is still positive on this side, okay? So the important thing here is we're now separating the real number line into regions, different intervals. And in order for the inequality to be satisfied, we need both of them to be positive or both of them to be negative. So because x is negative in this region from -2, or sorry, not from -2, from -infinity to 0. From 0 to 2, from 2 to infinity. This one's out of the running, and so is this one. So 0, 2, and we just have to make sure, can we plug in 0, can we plug in 2? We have to check the endpoints, okay? Can we plug in 0? And the answer here is yes, we can. Okay, so this is actually going to be a solid line. So we can include 0. What about 2? Can we include 2? We cannot. Why? Because if we plug in 2, then that makes the denominator equal to 0, so that's not allowed. All this is to say the domain is the interval 0 to 2, including 0 but not including 2. And that's the domain of f. Okay. Now, we just have to talk about composition. So for composition, again, we're doing this using two different functions. And we're going to define it a little bit more accurately here. We're going to have to be very precise, surgical precision here. So if the domain of G being some function, contains the range of f, define G composed with f to be the function such that for all x, we take G of f of x, okay, for all x in the domain of f, okay? And then similarly, we can define f of G of x to be f of G of x. So the way you want to imagine this visually, right? There's a couple of different ways of imagining this. So suppose this is A, the domain of f. And then the range of f is B, which is contained in this larger domain of G, and this is the range of G. Okay, so f takes elements in A, takes them to B, and then G takes elements in C and takes them to D. F and G. Okay, so this some x value, x, right, gets mapped to f of x, and then this f of x gets taken to G of f of x. Another way of thinking about this is you have some starting input x, and then you pass it through a function, f, so it goes through, and it comes out as f of x. Then you have some other function, g, and it comes out of that as g of f of x. So the y value for f is now the input for g. Let's work with this. Let's see some examples. So number one, find f of g when f of x equals square root of x plus 1 and g of x equals sine of x. Okay, so how do we find the function expression? So remember, f of g of x is put it through g first and then through f. So when you put x through g first, you get sine of x. So f of sine of x for all x in the real numbers. So for all real numbers, this part is true, right? And then if you put sine of x through f, that means wherever you see x in f, you're going to put sine of x. So this is going to be square root of sine of x plus 1. Okay? Provided that the radicand, what's underneath, sine of x plus 1 is greater than or equal to 0. So we would just need to worry about that, right? When is this not, is this inequality not hold true? But the nice thing here is that actually this is true for all x. So the domain actually is unrestricted. It's very nice. Okay. 2. Write two functions f and g such that g of f of x is equal to absolute value of x minus 1 all over absolute value of x plus 1. Okay, so what you want to do is you want to identify inner and outer functions. So remember that g of f is actually apply f of x first and then g. So our inner function is f. And g is our outer function. What helps is looking inside the function definition and seeing if there are any statements or expressions that repeat involving x. You'll notice one of those is absolute value of x. So absolute value of x is repeated inside the expression for g of f of x, which suggests that the inner function is the absolute value of x. And then the outer function is, ignore now the fact that there's an absolute value bar there. So that those y values are going into this other function, which is going to be x minus 1 over x plus 1. And then when you compose them, if you do it properly, you'll see that you actually do end up with what you started out with. All right. So function composition doesn't get too much more complicated than that. Of course, you have to be careful with questions of domain and when you're allowed to do things like that. That said, this does come up again, and it's really important that you get this down.